Who would have thought that ancient coins are connected to nuclear chemistry? I certainly didn't. And I wanted to introduce to you the XRF as a measurement method. XRF stands for X-ray fluorescence. We know from gamma measurement in nuclear chemistry that every radionuclide leaves a certain fingerprint in the gamma spectrum. It's similar with X-ray fluorescence. First, I'll introduce the measurement method and using pure elements. Then we'll move on to the composition analysis of modern coins, and finally, we'll take a look at the XRF as an analytical method for the often complicated metal alloys of ancient coins. For this, we are changing the setting today and visiting the coin collection of the Department for Classics at the University of Cologne. This collection is overseen by Professor Dr. Stab, who, together with Malte, will guide us through the measurements. Of course, I've brought some samples from home. Here we have some titanium. The best approach is always to cover the flattest area possible. Otherwise the geometry factor becomes significant, and we generally wanted the machine to do as much as possible and do as little as possible ourselves. And there it is. After just 1 minute, a spectrum. How do you read it? Where do the signals come from? Is it meaningful? As with other spectrum in nuclear chemistry, we have counts plotted logarithmically against energy. But the energy range is not longer in the 100 to 1000 kiloelectron volts, but in the single or double digit range. After all, these are X-rays and not gamma rays. I'll explain this now by using the first prominent peaks, the titanium K alpha and the titanium K beta line. By accelerating electrons in a vacuum tube onto a rhodium plate, X-rays are generated when the 500 kilovolts accelerated electrons hit and decelerate upon contact with the material. This also works with molybdenum and copper and so on, but in this camera, rhodium is used as the anode material. There are 30 microamperes of electrons flow. This is the sweet spot for fast measurement and low dead time. Now we have X-rays with enough energy to eject even the most tightly bound inner electrons from the K shell of most elements. Now we know why it's called titanium K, and the alpha describes which higher shell fills up this gap. In this case, it's the directly overlying L shell. This electron is more tightly bound and releases a characteristic X-ray line according to the energy difference between the L and the K level. This happens almost instantly after the gap is created, which is why it's called X-ray fluorescence. The energy depends on the electron's attraction of the nucleus, i.e. the nuclear charge. In other words, the element. Elements are defined by their nuclear charge. It also depends on which shell fill up these gaps. When the electron falls out of the M to the K shell, the energy difference is greater, and so is the energy of the K beta line higher. This is why this line is further to the right in the spectrum. Titanium has a nuclear charge or atomic number of 22, so it's very light, and the K lines are in the very low energy range of this spectrum. These two signals will always appear because they are the rhodium K alpha and K beta lines. Rhodium is the anode material, and X-rays are generated in this material, meaning that some rhodium atoms can also be excited and do X-ray fluorescence. I just mentioned K lines, but there are also other X-ray lines. But for that, we need heavier nuclei that attract electrons so strongly that the transition from the M to the L shell is energetically high enough to fall into this X-ray range. Cesium, for example, has L alpha and L beta lines, and when the electrons fall from the L to the K shell, even more energy is released, so the K lines appear in the very high energy range of this spectrum. Cesium has an atomic number of 55, rhodium of 45 and rubidium of 37. And then there's potassium with an atomic number of 19. And for those who have memorized all the alkaline metals, the rubidium line can also be explained. It is the lighter chemical homologue of cesium and can only be separated from it with a significant effort and chemical separation processes. So there are some traces of rubidium inside of my cesium ampule. Since the measurement device can also detect relatively minor impurities, they appear in this spectrum. Of course, we couldn't measure pure cesium, but we measured through a glass vial. Glass is essentially made up of silicon and oxygen, but when the device is set not to ignore the resulting silicon lines, you can see that mostly silicon is detected. But of course, our cesium is also present. When silicon is deliberately ignored, we arrive at cesium contents of 91%, but more on that later. Further down the periodic table, we have thallium, which has such a high nuclear charge that the K lines are too high in energy for this device to detect it. Therefore, we can only see the lower energy L lines. And for safety reasons, this was measured also inside of a glass vial. Now onto the application of modern coins. What's actually inside of a 10-cent coin? It's Nordic gold. 89% masked by copper. Yes. 5% aluminium. We'll get to that in a moment. 5% zinc. Yes. And 1% tin. That fits too. Even surprisingly well, to be honest. But where's the aluminium? See, here I have a coin found when I was a child while digging up in the garden, and apparently it's 99.8% aluminium, but its very low energy K lines push the device to its limit of what's possible. For aluminium to thallium everything works, but these two elements are just right at the very edge. And I'm just a poor student, but I saved up a whole euro for this video. The great thing about the euro coins is that they have a core and a ring. The ring is made up of 75% copper, 25% zinc and 5% nickel. And as you can see, all these things can be measured with this device. And I find it very fascinating how accurate these values are compared to literature. Yes, it's Wikipedia, but still, it's a nice overview. The core also matches up with 73% copper, 25% nickel. And now onto the ancient coins. This is where the XRF really shines as an application. And since we're now expert on the theory of X-ray fluorescence, we can sit back and watch the measurements of the coins. Which coins are being measured today? A drachma from Egypt dated to 135 AD, a tetradrachm also from 124 AD, another silver tetradrachm from the Ptolemaic times, much earlier from the 1st century BC. And of course, there are gold coins in this collection, including the one from Constantinople, dated to be between 976 and 1025 AD. I will go into more detail about these coins after the measurement. Here's what goes on behind the scenes during this measurement. We use LED glass to protect ourselves from the X-ray fluorescence, which does not only go into the detector but radiates in all directions. This measuring device is great because it's portable, and look at the measurement time. It only takes 60 seconds. When we measure, you hear a warning beep and a light signal indicating warning X-ray radiation. And we pretty much immediately get a spectrum, which is awesome. The drachm, according to the analysis software, consists of 85% copper, 10% tin and 4% zinc. However, we know that this coin is also made out of leaded bronze, which, while the lead is detected, this software doesn't analyze it. Now I have to address the fact that the coins don't have a perfectly smooth surface for measurement. All these values should be taken with caution as they haven't been corrected for absorption. With different metals, as in this case, additional absorption of X-rays can occur which significantly affects the percentage composition. For example, when lead is excited, its X-ray fluorescence can excite also additional copper fluorescence, which artificially raises the copper percentage and lowers the lead percentage. However, a correction factor can be determined for this problem. The fact that an alloy of ancient coins isn't always homogeneous can be addressed by just taking multiple measurements and calculating on the average. Since we know it's an impure bronze coin, the software can be adjusted. Using advanced analysis, we can specify additional elements such as iron, lead, silver and gold, prompting the device to search the spectrum for these elements. Especially with lead, as mentioned earlier in the video, the device struggles due to the high energy of the lead lines. The tetradrachm, supposedly made of silver, contains surprisingly low silver with just 37%. It just needs to look like silver, right? Experts call this alloy designed to look like silver while using as little valuable material as possible, Billon. Our modern 1 to 5 cent coins aren't made entirely out of copper either, just enough to appear to be so. Apparently, it's a 1,000-year-old tradition. The Ptolemaic tetradrachm, on the other hand, is much more like silver because it contains 91% silver. And the gold coin from Constantinople has 91% gold content, so it's indeed a true gold coin. Now let's talk a bit about the coins and the periods where they came from. The drachm, made from impure leaded bronze, dates back to 135 AD and comes from a region we now call Egypt. During the imperial period of the Roman Empire, Egypt was a province. The so-called silver coin, actually a Billon coin, is 10 years older, dating to 123 to 24 AD. It's a tetradrachm and it's designed to look like silver because nominally it was worth more. It was valued at 4 single drachma, hence the name tetradrachm. This coin also comes from the Roman imperial period. The genuine silver coin is another tetradrachm, but it comes from a different era, the 1st century BC. This was before the imperial period, when present-day Egypt was not yet a Roman province, but it was a part of the Ptolemaic kingdom. This coin contains 13.2 grams of relatively pure silver. In terms of material value, that would be just about 9 euros in November 2023. Back then, however, such a drachma represents an entire day's wage or the cost of 4 liters of oil. Of course, such conversions are complex, but they give a better impression of what could have been done with such a coin at that time. Finally, we have the gold coin, a Byzantine solidus. The Byzantine Empire emerged from the Eastern Roman Empire with its capital in Constantinople, modern-day Istanbul. This coin features a bust of Christ. The Byzantine solidus was recognized throughout the Mediterranean area. With a weight of 4.38 grams, it corresponds to a gold value of 257 euros as of November 2023. And to summarize, XRF is a highly suitable method for analyzing thicker objects such as coins, but only if it's done correctly by addressing issues like inhomogeneity with multiple measurements and incorporation of correction factors. A big thank you goes out to Professor Dr. Gregor Stab from the Department of Classics and the Research Group for Analytics and Fundamental Nuclear Chemistry, led by Dr. Erik Strupp. This all was filmed at the University of Cologne, and of course a big thank you goes out to my Patreons. With that being said, thank you for your attention and goodbye.